So as you have seen already, I will talk about the habitability of Mars and go from a different perspective as we usually do. It's more from a geodynamical or geophysical perspective. And okay, that's good. So you are probably more familiar with the habitable zone, where the orbital distance is relevant, where liquid water is present on the planet's surface. And what you see here is for different, let me see if I can get the pointer. Do you see the pointer? Oh, you see it here, right?
Yes, yes, we do.
Okay. It's on the different slide. Okay, so what you see here is for different suns, G star and M star and so on, the habitable zone. And at the top you see Mars, Earth, and Venus. But this is not the end of the story, because the planet itself plays a major role in determining whether a planet is habitable or not. And what you see on that slide is an introduction in showing the different reservoirs and how they are connected with the story of habitability, basically. Here is a sketch showing the mantle providing volcanism and outgassing to the atmosphere, important for plate tectonic planets, and that is the case for the Earth. We have subduction, recycling of volatiles, and also enhanced cooling. This, on the other hand, will introduce a cooling of the core, will introduce dynamo action, and that will then provide a magnetosphere which can shield the atmosphere and the biosphere. I have to say at that point that for the atmosphere, there's a debate whether there is actually, the magnetosphere is actually helping to protect the atmosphere, or even more enhancing the loss of the atmosphere. But anyway, that is a general picture at the moment, that the magnetosphere helps habitability on the planet. So if we go now to Mars, which is a one-plate planet, this mechanism of efficient recycling from the crust into the mantle is lacking. What does that mean? So we have here a one-plate planet where we have only a supply from the mantle into the atmosphere, but no recycling mechanism. And also we don't have this efficient crustal recycling and cooling of the interior. It is possible that, that core cooling is not that efficient, and a dynamo is not active anymore. And this has then the consequence that, coming back to the point I've mentioned earlier, that which is not certain, but erosion by solar wind and impact is, solar winds in particular, is then more efficient. So the question I want to address in that presentation here is how a planet like Mars, with a stack-and-lit scenario, how this can be habitable, where can it be habitable, and what has been changed in time for that planet. So when we take a look at Mars, we know Mars was a water-rich planet and a water-rich one-plate planet, so it has no recycling. We have early shows signs of surface water. You see examples here for deltas, flow structures, lakes, also hydrated minerals at the surface. Probably we had even oceans. And there is an estimated amount of past surface water between 100 and 1,500 meter. GEL means global equivalent layer. That was not necessarily at the same time at the surface, but it was necessary to create all these signs we see at the surface. And on the other hand, we know Mars today is totally dry, cold, and has a very thin atmosphere. The question is, one question is, did we have a thick atmosphere at the time to produce a warm and wet atmosphere? So we had long-standing water at the surface, or was it more a period which was still cold but wet? So we had short episodic supply, for instance, from the interior by volcanic activity to activate molten ice in the interior to produce these features. And one way is to to go back in the story and look how much can we outgas in the case of a one-plate planet. And that's illustrated here again, that we have now a one-way mechanism of outgassing, but is that sufficient to provide a very thick atmosphere, or is something else going on in the case of Mars? So to start, we have actually to look, what do we know about the volatile delivery when the planet was formed? And there are some accretion models. Here is one example by Brassel et al. From 2013 and Walsh et al. 2011. They first show that Mars can accrete. It was always a problem to produce a small planet in that location from the solar system. But what they show, and what is important for my presentation here, they show that Mars was accreted with water, and they assume an amount of 0.1 to 0.2 weight% of water, which is equivalent to 3 to 6 kilometers of this global equivalent layer. So that's a lot of stuff, which would, you think, okay, that's great. We can explain why there was a lot of water at the surface. Now comes the problem that although you bring a lot of volatiles, water and also CO2, I come to CO2 later in my presentation, but we have also important phases of the Martian interior where we lose water, and it starts with the accretion and core formation in the magma ocean phase. They said, for my second part of my presentation, they set actually the initial state. So we are interested here in the volatile distribution between the interior, the atmosphere, and also what is lost to space, so which is gone from the system. And when we know that, we can continue and look at the long-term thermal evolution, which includes volcanism, outgassing, and also magnetic field generation. Although I will not touch about magnetic field generation because it would be just too much to include that as well. What you see on the figure here is time frame for several activities for the Belle networks that was at the time of Noachian, Hesperian, and Amazonian. We had a long-standing volcanic activity, actually probably up to present day, although only in a few locations, but that was active. But we have a very strong volcanic activity early in the evolution. There was some basin formation of Hellas, Agyre, maybe you've heard about that. That is important for the magnetic field generation, because in these regions, we do not see remnant magnetization of the crust that suggests that there was either no magnetic field or something strange was going on. Okay, I don't want to go much more into detail of that. I want to continue about the water issue. So I just said there was a lot of water coming to the system. There are several possibilities. First, we had kind of a dry accretion. So the first material which arrived was dry. We had a core formation, and later on, there was a volatile rich planetesimal, whatever, what brought all the water, and then you had an atmosphere and you had probably water at the surface. Another possibility is that you have accretion of dry and wet planetesimals, what is illustrated here, but at the same time of core formation and other processes, all the water is released, efficiently removed from the interior, and is at the surface in the form of atmosphere or water, but the interior is dry. The next one is you start again, you have accretion of dry and wet planetesimals, but the outgassing is not efficient, and that would mean you start with water in the interior, and then you have the chance to degas later on in the evolution. So we have these two scenarios basically. The first two end up that you have a formation of an early dense atmosphere with respectively dry interior, or you have still some water in the interior, perhaps a thinner atmosphere and water at the surface, but you also can substantially supply a secondary atmosphere. The question is now, what is relevant, what is the case for Mars that we are going to discuss? So now, how efficient is a secondary outgassing, and can we, with our models from the interior modeling, can we contribute to the question whether there was a warm and wet atmosphere, meaning long-standing water, or was it kind of a cold and wet atmosphere, more like episodic water flow, to explain the features what we see on early Mars? So we have answered already, not answered, but we addressed already the volatile delivery, where we see, okay, there was some water coming and not no, I don't know the English word, but so a lot. And but we have, and that's what you see now, we have a strong loss of this early water due to several effects. That is first impact dehydration, oxidation, and magma ocean solidification. I'm going to show you first the impact hydration. There's several studies about that. Here is one example from Tubucci et al. 2001. So when you accrete the material and you have already planetesimals that contain some water, as the planet is growing and the impact velocity increase due to the increase of mass and increase of radius, first you lose a little bit of water, and at a certain radius you lose basically all the water. That's what you can see here is the impact-induced devolatilization. And here is the radius as a function. So this is the surface radius, and this is the center. So and in the case of Mars, you see that the volatilization starts approximately, if you recalculate it to the kilometer radius, from 340 to 1,000 kilometer, and complete volatilization at 1,700 to 3,000 kilometer. That suggests that you have a decrease of the water content toward the surface, and you have a efficient volatile loss into the atmosphere already doing the accretion. There is one way out in the sense that we can save some water, trap some water in the interior. They have some recent experiments where they did impact experiments where they show that approximately in these ones here, 30% of the water in the impactor was in two reservoirs. It was first in the impact melt and projectiles that survived basically. So there is a way that we can trap water in the interior also when they grow, when they get larger. So it's not helpless to start basically with non-water. Yeah. Because there is another problem for water, I must say, that we also lose volatiles or water in that case before the core is formed, because there is kind of oxidation where when you have water in reaction with metallic iron that forms to FeO and H2 gets released and goes also in the atmosphere. And some of the hydrogen can go into the core, but before core formation, you lose basically a lot of the water. Some people assume that you basically lose everything. So before core formation, you can't store water in the interior. So that's the second process where you lose a lot of water. And we come now to the third, which is also very efficient, as you can imagine, to lose water. That is a magma ocean crystallization. That works like this. You can see on that figure here, that is there's a temperature as a function of radius, a typical accretion temperature profile. So when you accrete material in the interior, it is cool. Then you hit with more particles, and that heats up the outer shell so that the temperature is increasing while the body is getting larger. So, and the melting temperature is typically pressure dependent. So closer to the surface, the melting temperature is lower than deeper down. So it increases with pressure, and pressure is increasing in that direction. So that means that close to the surface, you produce melt. And that is typically when you produce people assume that that there was a global magma ocean of larger bodies. Yeah? And Mars would be one case. That how deep it was is not clear. Estimates range from 500 to probably also the entire mantle. But anyway, it's likely that there was kind of a magma ocean on early Mars. And what happens when the magma ocean crystallizes? Typically, it crystallizes from the bottom to the top, also because of the temperature profiles and the melting temperature. So it crystallizes in the bottom. What happens is that volatiles, actually similar to radioactive elements, are continuously enriched in the melt. So The solid part is growing, the liquid part is shrinking, but melt goes into the melt. Not melt, volatile water goes and CO2 goes into the melt. And by vigorous convection, it reaches the surface where the saturation is very low. So it can degas into the atmosphere. And it is very efficient and happens very rapidly because the crystallization of a magma ocean typically is in the order of a million years, something like that. So it's very efficient. One way to store a little bit more of water is depends on the solubility again of volatiles, because they depend on pressure. When you take a look here, here's the pressure. Here is the percentage of volatiles remaining in the basalt. Is given for sulfur, water, and CO2. And assume a pressure of 10 bars. What you see here is that CO2, because it has a very low solubility, goes directly into the atmosphere, but water at 10 bars is still stored in the melt. Yeah? So to get rid of water in the melt at that pressure, you need to have more water in the liquid phase. As a consequence of that is what you can see here. Okay, for high atmospheric water, more pressure remains in the interior, or degassing is retarded. That's what you see on that slide here. This has been actually calculated for the Earth, but it is a similar scenario on for Mars. What you see is the outgas volatile pressure as a function of time when the magma ocean crystallizes and solidifies. So what happens at the first time step, basically, that CO2, because it is not restricted by the solubility that much, outgases immediately. So you have a very dense CO2 atmosphere. Because water is much more dependent on pressure, the pressure here is too high, so water still remains in the liquid. You continuously to freeze out means you enrich the melt until a certain threshold where you then degas water. So with other words, during the mechanism of magma ocean crystallization, you have initially a very dense CO2 atmosphere, and later on you also outgas, in this particular case, even more water, and then you have a dense CO2 and H2O atmosphere. To make that into a more into number is that when you do these models, you see typically that you have an outgassing efficiency. We just talked about the magma ocean now, about 59%. There is a possibility that volatiles can remain in the mantle trapped in melt. And there the value ranges between 1% and 2%. But at the end, when we add everything together, what we just discussed, that there is not much water left in the interior. Yeah, we started with 0.1 to 0.2 weight% of water due to oxidation, due to the accretion process and the magma ocean solidification process. We lose most of the water, and we can only roughly estimate that it's something between 90 to 95%. To get a better idea whether these scenarios are realistic comes from meteorites. And in the case of Mars, I mean, it comes from meteorites. There are estimates from SNC meteorites, and also a composition model by Dreibus and Bernke, where they get some numbers. What is a primitive water content in the interior? And it ranges from very dry, from 36 ppm, that's not much, to something like 52 to 220 ppm water in the interior, but which is still equivalent to 100 to 600 million meter global equivalent layer. And if you remember what I said, to explain the surface structures, something like 100 to 1.5 kilometer is requested, although the upper values are more likely, I have to say. So we end up with a relatively dry mantle, but we have a dense primordial atmosphere, which you later will see can also help. So in the specific case by model by Elkin-Stanton and Oda et al., they calculated that the primordial atmosphere has a pressure of H2O between 50 and 100 bar and of CO2 of 100 to 22 bar in that range. You remember today we know the atmosphere has 7 millibar. We have to get rid of that atmosphere. But this obviously, oh no, before I go to that point, is another, I think, an important issue for the distribution of volatiles in the interior, probably not only for Mars, also for the other terrestrial planet. But it's very likely that, okay, we have now the dry mantle, we have a very steam dense atmosphere, but during that process of the loss processes, it's very likely that the early, I would say deep crust, because you need intrusive melt, that is enriched, the last silicates or the last minerals that form, they're typically enriched in water. If you remember that during the solidification process, water goes into the melt, and the last minerals basically that form at top, they have a lot of water. And there is a possibility that if it is kind of more intrusive melt, that this water gets stored because it cannot release to the atmosphere and may form hydrated minerals. And another idea is, that is from a paper of 5 years now old, by Cannon et al. They show that when you form a primary crust, it can react with a dense steam atmosphere to form clay minerals. And they assume when you have a porous layer, for Mars, it's assumed like 10 kilometer thick, that this porous layer was formed in a time scale of 10 to the power of 7 years. But it is what, 1 million years, or less than 1 million years. And this layer has then, by impact and volcanic eruption and so on, has been hidden underneath the surface, so that is not visible because we don't see that many clays on the surface of Mars. So with other words, it's likely that we have a crust with, which is actually not dry, but which is relatively water rich. And we see later from thermal evolution models, there's actually a strong indication that this is actually the case. And that is one reservoir in the case of one-plate planets, in the case of Mars, to store a lot of water. So we come now to the question, what happens actually to this early atmosphere? Because the situation is not that easy that we say, okay, we have the dense atmosphere and everything is fine. That means, okay, we can have high temperature at the surface of Mars, and to explain the all the surface features. The issue is that we actually lose this primordial atmosphere very rapidly. The reason is that we have a strong XUV activity of the sun that you see here. That's the activity as a function of age, of time. And it is very strong during the first billion years, 200 million years, not billion years, and is then decreasing. The consequence is basically what I just said, that you lose the primordial atmosphere in timescales of 18 to 25 million years. So very, very fast. And that comes to the situation now that, maybe I'll show the next slide here, that we have first efficient outgassing, we have the dense atmosphere, we have the enriched crust and a relatively depleted mantle. But we lose this atmosphere extremely fast due to the XUV and of the young sun. So now comes the next point. How do we supply? So we end up with basically non-atmosphere, and we have to supply now CO2 and water and other gases from the interior of the planet to produce a secondary atmosphere. And this is something we have looked at. So what we are discussing now is what are the main processes that influences volcanic outgassing, and come back, I mentioned it already several times, the point about long-standing versus short-term and episodic water supply at the surface. So how to change the volatile content in the interior? Oops, what is this? So when the mantle rock is partially molten, I've mentioned that, volatiles go into the melt, then melt is transported into the crust, so it rises due to its buoyancy, and some of the melt will erupt and will degas. So in volatiles that are embedded in the melt will be outgassed, and then the atmosphere is enriched in volatiles. And if you remember what I said, melt, which is intrusive, that will not supply that much to outgassing, because the gas cannot escape and it will remain in the crust. So it's also important for outgassing, how much is the extrusive rate and how much can actually outgas. So to do that, there is a model where we calculated from a mantle reservoir this outgassing. So what you need to do is to calculate the rate of volcanism, or the crustal growth rate, what you see here. Then it is scaled with outgassing efficiency. That means basically how much of the crust or the melt you produce is extrusive and can contribute to outgassing. And most important is the concentration of the volatile species in the melt, either of H2O or CO2. And this is the interesting part, because this is different for H2O and CO2. And the amount of volatiles depend on two factors. That is the solubility in the melt, and is the partitioning of the volatiles from solid into melt. And the limiting factor, so the process that allows the lowest amount of volatiles in the melt, determines basically the volatile content which goes into the melt and then can release into the atmosphere. And as I said, that is different for CO2 and water. So what you see here is the solubility for water. And water is extremely highly soluble in magmas, yeah, apart from the surface, what I mentioned earlier. So during the magma ocean crystallization, when magma comes close to the surface, water is basically gone unless there is a thick atmosphere. Okay. But for melting in greater depths, for instance, 100 kilometer depths, you can 15 to 20 weight% of water can be soluted in the melt. So it's a lot, and there is not that much available actually. If you remember, we're talking about around 100 ppm water in the mantle. It's going automatic here. Let's see, what was that? Okay, I had that. So, well, I said the solubility, a lot of water can go into the melt. So the factor which limits then how much water really goes into melt is the partitioning of water. What you see here is the melt fraction, the water in the melt, and here is the degree of partial melting. And for different compositions in the mantle, 10 ppm, 100 ppm, 1000 ppm. So that is for 1000 ppm, that is for 100 ppm, that is for 10 ppm. And assume now you have partial melting. You have partial melting of 10%. That means for 100 ppm water, 0.1 weight% goes into the melt. And this is much less if you remember how much is soluted in the melt. That was in the order of 10 weight%. So the determining factor is the partitioning coefficient, which is very low for water, is 0.01. And this becomes important. So, but let's first go to the solubility of CO2. CO2 is dissolved in melt as carbon ions. And the interesting thing is that the solubility of CO2 depends on the oxygen fugacity of the mantle. And for Mars, the oxygen fugacity is around typically the iron Wüstheit buffer ±1. And what that means is what you can see on that figure here, that's the melt concentration for CO2, the CO2 concentration in melt. And this is again the melt fraction, 0 and 50% of melt. So how much CO2 goes into the melt is not very much dependent on pressure that you see here on the different lines. And it is also not that much dependent on the melt fraction, but it is strongly dependent on the oxygen fugacity that is listed here. On that figure is only given for iron Wüstheit buffer. So there, for 10% of melt, you have 100 ppm. For 20% of melt, you have 120 ppm. So it's no big difference. But if you increase the oxygen fugacity to +1, you get a factor of 10 higher concentration of CO2 into the, which goes into the melt and can then leak out gas. So that means that we have two different ways of outgassing. So for CO2 or for water, it depends on the initial content of the in the mantle. It depends on the partition coefficient, which is very small for in the case of water, and it depends on the degree of melting. In the case of CO2, that depends on the oxygen fugacity mainly. That's basically in the case of Mars, these are the typical values of iron Wüstheit buffer and iron Wüstheit buffer +1. So for higher oxygen fugacities, the partitioning would be similar to water, but this is obviously not the case for Mars, as it is indicated by Martian meteorites, yeah, that we are more on the reducing side. And this has strong consequences on the outgassing, but before I come to that, I want to mention that water in particular has not only the effect of getting water out in the atmosphere, having surface water and so on, it also strongly influences the interior dynamics. And this is important when you want to couple the interior with the atmosphere and so on. So first, the metal water content has a strong influence on the melting temperature and the melting and the mantle viscosity. But what you can see here as a function of pressure and temperature, this is a melting temperature for a dry mantle, and if you have water, the melting temperature is strongly decreased. The point for Mars is, because we talk about values about 100 ppm, the reduction in the melting temperature is minor. So for Mars, this effect of solidus reduction is not important. That is very important for Earth and for plate tectonic planets, but it's obviously not important for Mars during the entire evolution. The situation is different for the rheology, because a little bit of water in the order of a few tenths of ppm can reduce the viscosity by several orders of magnitude. And if you imagine, for those who are not familiar with dynamical processes in the interior, if you have a low viscosity, it means you can have much stronger convection, and you can have then more outgassing, you can have more stronger cross production, you can stronger cooling of the interior. So there's a strong consequence actually that we will see later, I think, on one slide. Okay, so just to have in mind, for Mars place, water in the mantle does not play a role on the solidus temperature, that it will be reduced, but it has strong consequences on the viscosity. Okay, so what we see here is now a model where we calculated the outgassing to fit several observations. The story here I want to make is how much can be outgassed during the evolution. And we have two extreme models here. One is the global melting model, and one is the plume model. That basically means in the first case here that we have a global melt zone, which is decreasing, or which is increasing with depth and disappears already relatively early, but we have melt fractions of, what is that, relatively small melt fraction, but it is globally, you know, underneath the stagnant lid. This is one extreme. In the other extreme, we have a plume model where we assume melt is only produced in the plumes, and which covers approximately 1% of the surface. And in that case, I should mention that both models produce the same crust thickness, the observed we have from inside now, so we know approximately well what is the thickness of crust. So those models need to fit the present day crust thickness. But what you see is that the melt production is prolonged, but we have different melt fractions to explain the same crust. Yeah, so the two extreme, and we look, how does that influence the outgassing story of Mars? And that you can see on that slide here, that is the atmospheric pressure as a function of time for those two cases, for the global model and the plume model. The green lines here gives the equivalent global water layer, and the black line gives the atmospheric pressure due to CO2 and including water. No, I think without, just of CO2. So the difference now is that the global model in comparison to the plume model, although the crust thickness, and it proves basically the same amount of crust and melt, produces a much, or start with CO2, produces basically the same outgassing of CO2 of 1 bar in that case. Yeah, but for water is different, because the plume model get rid of much more water than the global, no, vice versa. The global model produces more water than the plume model, because the degree of melting was smaller, also in a smaller short of time, but the if you remember that the partition coefficient is relevant here, and the degree of melting, for a smaller degree of melting, you have more water in the melt, and you can release more water than in the case of a larger degree of melting, producing the same amount of crust. I think that was chaotic now, but you can pass me later. But the story here is that you can only outgas CO2 of maximum 1 bar, yeah, for both extreme cases, to put it this way. And this is already for oxygen fugacity of iron Wisted buffer +1, so the upper limit what we assume for Mars. So with other words, to the outgassing of the interior of Mars with all maximum assumptions you can do is not much, is less than 1 bar. And assume that you lose the early atmosphere by the EUV radiation. The CO2 atmosphere at the end or during the evolution is even smaller. Yeah, for these extreme cases here, that is the iron buffer +1. The pressure is lower than 1 bar. It's actually lower than 0.5 bar and even lower. Yeah, because you lose early the atmosphere, that value becomes even smaller at the end. Yeah, because this phase, XUV phase, is in a range of 100 to 500 billion years. So you lose basically all this water. It comes to the point that, okay, it tells you what model here, that when we talk about the secondary outgassing on Mars, the optimum is that you outgas 1 bar of CO2 and 55 meter of this equivalent global layer of H2O. Assuming again this typical value of 100 ppm initial water content. The issue is that due to hydrodynamic escape, it not only get rid of the atmosphere due to the magma ocean phase, but it erodes also the early Noachian atmosphere. And that means there, when you have all these outward channels where you assume there was a dense atmosphere and high surface temperatures, the atmosphere we have is pretty low, small, and that suggests actually that the interior models favorite the cold and wet atmosphere and not the hot and wet, yeah, because there's certainly not enough CO2 you can provide into the atmosphere to get a dense, thick atmosphere to have high surface temperature and to have conditions of long-standing water. That is one conclusion one can make from interior modeling of stagnant planet, in particular here on Mars. Another point I want to make is we talked about the crust, whether it was wet or it is dry, and whether that can be an habitable reservoir. And interestingly is we have observations of the elastic lithosphere thickness for different times that you can see here. That is a function of time, that the elastic lithosphere thickness, those dots, have been derived by gravity topography measurements. So what two important points here. The early values are very, very low, and they can only be explained if there was a rheological wet crust. And I've explained already the scenario how you can produce such a crust. And these evolution models basically require such a crust, which is good. On the other hand, we have very high thick elastic lithosphere thicknesses at present day. They have been derived at the northern polar cap, also by gravity. That's from radar measurement. They show the deflection of the surface, and they show very thick values. The point here is to explain those values, you need to have a present day dry mantle. This has several consequences. That means the estimates we have from meteorites, if you remember, that varied from 50 to 200 something ppm, it's more likely that is in the lower range and not in the upper range, because otherwise you cannot dry the mantle up to present day to explain those thick elastic lithosphere thicknesses. Yeah, so that comes back to the story. In the beginning of the evolution, due to the magma ocean phase and accretion and so on, we lose most of the volatiles from the interior, store water in the crust, and have a very thick atmosphere, which also, or let me, maybe I go through the slides here, so that these are finally slides to repeat actually what I've said. So we had water signs at the surface of 100 to 1,500 meter at the surface. And it's a question whether it is warm or wet, long-standing water, or we had more episodic water flow. The accretion models suggest that we had a lot of water there, so it shouldn't be a problem. But the issue is that we lose most of the water to several processes, and we have basically a dry mantle. We have a crust which is very enriched in volatiles, can be either due to interaction of the crust and a dense atmosphere, or due to intrusive melt, which was early likely be enriched in volatiles. And we have this primordial, very dense atmosphere. But this dense atmosphere is rapidly lost. Yeah. And the problem is now how to supply the secondary atmosphere. And here it looks like there is not much CO2 you can outgas, which would then support the cold, wet Martian atmosphere. This is actually also consistent with atmosphere loss models because they show that it's very difficult to lose a lot of CO2 in the last 4 billion years. They're from ESCAPE models, so that would fit with this story as well. And these models suggest also a wet and weak crust, but a dry present mantle, so that it also goes into that story to explain the elastic lithosphere thicknesses. And the thermochemical evolution models support actually the habitable environment in the Martian subsurface. I think that was one of the talks, I don't know, a couple of weeks ago that you had in your seminars. And with that, I'm finished. Thank you very much. Should I stop the presentation or how you can